Okay, so now it's time to listen to Bas Schouten. I'm sorry for the pronunciation. I don't know. Okay, thank you. So Bas is an engineer in the Mozilla's graphics team. It's him who has implemented a large portion of the code needed for Windows in GFX. Bas is also very much involved in the Mozilla community, creating a real Dutch-speaking community to bring together Dutch, like him, and Dutch-speaking Belgian. So please welcome Bas.
That was a lot more than I claimed credit for, but sure. Right, I am here to talk with you about utilizing GPUs to accelerate 2D content, which is mainly what I've been focusing on during my career at Mozilla. As was said, I work for the graphics team for Mozilla. I mainly work on Windows and acceleration on Windows, but I've also done, for example, the initial OpenGL implementations and things like that. So, I have a little disclaimer here. The market and the technology in this area moves very fast. I'm going to make a couple of statements. If any of those turn out to be outdated, I'm sorry. Right. So, what am I going to talk about? I'm going to talk about why we want to use GPUs. I'm going to talk about the strengths and weaknesses of them, the challenges for 2D rendering, what the GPU pipeline looks like, the available approaches we can take when doing 2D rendering with GPUs or GPU-assisted 2D rendering, and existing implementations that are out there. Does everybody here know what a GPU is? Good, good, because that would have been a problem, right? So why do we want to use GPUs? Well, first of all, these days they're present in almost every machine. Where we need to make a distinction between discrete and integrated GPUs. Integrated GPUs you will find on your machine chipsets, or for example in the new St. Sandy bridge on the die along with your CPU. And discrete GPUs are separate chips which are either soldered on your laptop motherboard, or you can find them, you know, the nice bulky cards that you put into your desktop machine because you like gaming. Now, why do we want to use them? Well, they are called graphics processing units, so it seems to be sort of an obvious choice for the job. And what they basically do is they give us much better flops, floating point operations, per watt, and much better per dollar. I probably should have made that into euros. Too bad, really. So if we look at this market, the first 3D accelerator cards that were introduced in around 1997. And later, a very famous one was the Voodoo 2. The Voodoo 2 produced about 500 megaflops a second at a thermal design power of about 10 watts. It costed about $300, and it was a purely gaming-aimed device. There was absolutely no other use. It was really hard to use for anything else. Now, this means that per watt, you got about 50 megaflops per second. And per dollar, you got about 1.6 megaflops a second. That's not very great. Common CPU in those times was a Pentium 2. It produced about 233 megaflops if we take a specific variant of also the mid-section of the market. It had a thermal design power of about 17 watts. It costed $500. And you can see that the numbers there are, you know, less gigaflops per watt, less gigaflops per dollars. But the differences aren't as stunning as they are these days. Nowadays, you get a Radeon 6750, which is a discrete ATI GPU from about the mid-segment of the market, about a year or two back. That produces a teraflop, which is 1,000 gigaflops a second. It has a thermal design power of 150 watts. Note, we've become a lot more power hungry. Need to work on that, really. It costs only $100, which is a world of difference. Like, that's a price that's affordable in your average machine. Produces therefore 6.7 gigaflops a second per watt and 10 gigaflops a second per dollar. Now, if you compare that to a common CPU in these days, which is the Ivy Bridge i5-34575S, that produces a tenth of that at a higher price, at double the price, but lower power, unlike in the olden days. Anyways, you can see now that we have over 4 times as many gigaflops a watt per watt on the Radeon. And we have over 20 times as many gigaflops a dollar, right? So everybody likes cheap. Well, that's basically the why. Now we have to figure out how to do it. Well, what are the GPU's strengths and weaknesses? Most modern GPUs are triangle rasterizers. That means that when you have a game, the game will have models. They consist of triangles. And your GPU will help projecting those triangles onto your screen, essentially. They have a bunch of fixed function hardware to help with that. Fixed function hardware is basically, a chip that is designed to do a specific thing, so it's very good at that. For things like blending, which is basically, blending a transparent pixel over something else. Texture sampling, which is interpolating when you're reading from an image, when you want to size it up, size it down, etc. And triangle rasterization, because that's their business, right? Aside from this, they also have programmable shader cores. Now, on modern GPUs, these are just general floating point computation units, and they are used in several steps: vertex shaders, pixel shaders, geometry shaders, hull shaders, domain shaders. Those are the common ones that you see in modern graphics APIs. The pixel shader for OpenGL people will be called a fragment shader. Now, these shader cores, we can really let them do anything as long as it's basically 4-component math. So these are the strength, right? They're really good at drawing triangles. When you have a discrete GPU, they have an immense memory bandwidth, much bigger than your CPU does. They are very good at parallel computation, because these cores by themselves are not that great, but you got 1,000 of them all running in parallel. Every cycle, every one of those 1,000 cores, for example, can do a bunch of computations. And they're, as I said, very good at 4-component vector operations. Now, why would they be very good at 4-component vector operations? Well, it turns out everything they work with is 4-component vectors. Now, that is pretty obvious when we're talking pixel manipulation. If you think of the red channel, the green channel, the blue channel, and the alpha channel, which is the transparency, you can see how I've noted down a simple blending formula for using the Porter-Duff operator over for blending a source pixel onto a destination. That's all 4-component vector math, right? But next to that, we also have vectors themselves, so points in 3D space, triangles. Now, one might say, well, we have x, y, z, right? So we only have 3 components. Why would it be 4 components? Well, turns out we add a little 1 to these vectors, and that means that when we can make a bigger transformation matrix, and we can have a fine transform, which actually in the last column also has a translation. So we can not only rotate vectors about, we can also move them on the plane, because we're actually talking points and not vectors. So this too, this matrix manipulation, multiplication you're seeing here is basically 4 dot products, right, of 2 4-component vectors. So this is basically all that they're doing, and that's why they're really, really good at it. So we want to exploit that, because they have a bunch of weaknesses. They have very poor branching performance. Like until very recently, you can write a shader and you can have an if statement. And you can say, oh, but I always hit this really simple path in my if statement. Problem is, it's going to run all the other paths as well, because there's no branch prediction. You won't, so it's just going to mask the result at the end, but it is going to run all your code. So your shader is as expensive as the very worst case that it can run. That's a problem. That's a big problem for a lot of things. They also don't have great serial performance. As I said, individually, these things aren't that great. There's just 1,000 of them. That's why they're great, right? Another problem, they don't have preemptive multitasking, which basically means once they go, they're going, right? And there's no way to stop them except give a big reset command to the whole thing. And then you have to set up everything again. It's not like you can switch context like we do on a CPU, right? People are working on that. It will happen in the future. At the moment, it's not there, though. So once you make a job that's too hard, you're absolutely royally screwed, because the screen is going to lock up because it can't do nothing else, right? So it can't draw the person's UI or anything like that. That's a disaster, right? Then the state manipulation is expensive. We have to we basically have to set the program on these cores, right? And you have to prepare everything for this task that you're going to set it out to do. And then you're going to fire it off. And when you fire it off, it goes into the GPU pipeline. Now, the GPU pipeline is going to do work, but it's a fire and forget mechanism, basically. So if I want the result back from that, I'm going to have to say, if I'm the CPU, right, I'm going to have to say, okay, now I'm just going to have to wait till the GPU is done. And I'll have to stall in order to get data back out of it. So reading back from these devices is very expensive as well. Basically, we need to make sure that everything we do goes to the screen, not back to us. We can't get it back, or we can, but it's infeasible, right? So that produces a number of challenges when using GPUs for 2D rendering. Well, something I haven't mentioned yet, but I will later on a little bit, is that high-quality anti-aliasing for us in 2D graphics is really, really important. In video games, which are very dynamic and you rarely have static content, right? You're moving around and things like that. If your anti-aliasing is a little bit lower quality, it's still pretty good. A lot of people play games without anti-aliasing at all. For 2D graphics, that's not an option at all. Everybody notices those jaggies when they're just standing still on your screen, and it's going to be a disaster. So we need to find ways to do high-quality anti-aliasing, either with the GPU, which really only high-end GPUs are able to do well, or we're going to have to do it with the CPU in different ways that I'll talk about in a minute. Now, the other thing they're bad at are frequent interactive scene changes. When I go into a room in a game, when I switch areas, etc., people are perfectly used to a loading screen, and that's okay, right? And you've got to upload all the new data, the new texture of the wall, the structure of the room, the structure of the characters that you find, all those things. But you can take your loading screen. You can do some, you can take your time. If I switch tabs, and everything changes, the text changes, the images changes, the shapes change, people aren't going to be very happy if they see a loading screen every time they switch a tab, right? So this model isn't that great for desktop applications. It's a problem you have to solve. Now, another problem is that these things are made to draw triangles. The way we describe shapes in 2D graphics, which is usually through lines and Bezier curves, that's not triangles. So we have to find a way to get this triangle drawing thing to work. Also, these things are used to having a model. You position things in space, and then you send it out to render. In 2D drawing, most APIs at the moment still work as an imperative drawing command stream, which doesn't batch very well. It's hard to batch them. And you want to batch, because as I said, state changes are expensive. So you need to do as much as you can in a single draw call. This is a hard problem as well. Finally, there's text. I'm already running late with my presentation. I wasn't going to talk about that because it's never going to make it in. But it's a very complex problem. If you want to learn more about it, I'm happy to talk to you about it afterwards. Right. So I promised to summarize the GPU pipeline. I'm taking the two most basic shader types, the vertex shaders and the pixel or fragment shaders here. I've taken out all the other ones because that would complicate things needlessly. Basically, the first stage in the GPU pipeline is the input assembler. It's where all the vertices go in, the index buffers go in, the instance buffer goes in. You basically give the GPU all the data it needs to draw your scene, right? Then you get the vertex shader. That's a stage in which the GPU will do these GPU cores will go to work on your shaders, on your vertices. Now, these vertices will then be, for example, transformed, moved around, et cetera, et cetera. And after that, they will reach the rasterizer. Now, the rasterizer gets these, after they're turned into triangles. The rasterizer will try to rasterize these triangles. But for each pixel, it will do a couple of tests. It will do a depth buffer test. It will do a stencil buffer test. If you want it, it'll do a scissor test. A bunch of tests, which are really cheap. At this point, you're not paying a price for a pixel. Now, if it passes all those tests, then the pixel gets filled, and you start paying for that pixel. That pixel will go into the pixel shader. The pixel shader has an opportunity to manipulate, to take the interpolated data from those vertices, from those triangles, and to change them into the desired output pixel. So it will output one or more pixels which have a color and a transparency and things like that, which will go to the output merger. And the output merger actually has read-write access to your destination directly, and it will merge your pixel onto the final destination surface, which will bring it onto a procedural texture or onto your screen. Right? So that's what the pipeline looks like. And now I'm going to talk about the different ways that we can use the pipeline to do 2D drawing. There's a couple of basic approaches. And these are really the fundamentals of what you can do, or what we commonly is done. The first one is convert your 2D shape to triangles. Right? I can make a curve. If I make the triangles small enough, I can describe the curve in triangles. Right? They have to be tiny triangles to get good quality, but it can be done. And it's a process called tessellation. Now, there's also rasterizing on the CPU, and then just doing your composition on the GPU, basically making use of that great 4-component vector math to do your sampling and your blending. Then there's 2D coverage computation in shaders, which is basically using your shader cores to do geometrical calculations. I'll talk about that. And then there's direct hardware implementations, which is basically something like OpenVG or NVIDIA's path rendering extension in OpenGL, which basically allow you to give your 2D geometries to something that is magically implemented by the hardware. First, tessellation. I have some examples here of how figures are tessellated. Now, the top figure, which consists of only lines, you could probably already see kind of how I could change that into triangles. And as you can see, it can be trivially made into having these 4 triangles over here. Now, the other shape has a curve on one side and then lines on the other, which means that you can take the inside and you can make that into a triangle pretty good, right? But then you have the outsides, and you're going to need to actually do the curve itself, and you need lots of triangles there. This is a very much an inflated one. You know, if you actually wanted to draw it this size, the amount of triangles would be much, much bigger, but obviously you wouldn't be able to see them, so there wouldn't be much of a point in showing a slide. And then if you get 2 curves, an even more complex shape, you can see that the triangles get more and more complicated, and you get loads and loads and loads of them to get sufficient quality. Right, so it has a couple of pros. First of all, there's no overfill within a shape. What basically means, you know, your triangles are covering the pixels that you actually want to fill. You're not running your pixel shaders for any pixels that you're not actually going to fill in the end, right? You're using the GPU as intended. It was made to render rasterize triangles. Once you have these triangles, you know, you're doing what it wants you to do. The shaders that you're using are very simple. They can simply sample for a texture, they can sample a gradient, they can output a color, you name it. It's very easy. You can do anti-aliasing using multi-sample anti-aliasing if you want, right? And multi-sample anti-aliasing is the standard method that most games use. As I said, works a lot better on high-end hardware than on mid-end or low-end hardware. Now, the downsides are that tessellation is hard. And it's generally the very best algorithms are big O, n log n plus k, where k is the amount of cell for intersections that something has, and n is the amount of line segments that your shape is subdivided into. This is all CPU work. So really, although you're losing a bunch of CPU work in the blending and the rasterizing and the drawing, you're adding a bunch of CPU work in generating your shape, which means if your shape is very complex, you might actually be spending more CPU work doing this than you would have in the first place if you would have just, you know, done the rasterization on the CPU. Also, anti-aliasing, if you want really high quality, or if your hardware doesn't support MSAA well, is a really hard problem. You have to make all these tiny little triangles for each pixel, and you get a resolution-dependent mesh. So you no longer have a nice triangle of your shape. You have all these fiddly little triangles that are just there as little tricks to make pixels look like they're anti-aliased properly. For some things, you can use the interpolators, do nice things, but in the end, it's a very hard problem. Now, the next method I'm going to describe is rasterizing on the CPU. This is pretty simple, right? You basically draw your shape in white into your stencil buffer, right? So your stencil buffer now has 1s for the pixels which fall within your complex shape and 0s for the pixels that don't. Then you upload, you know, that mask to your stencil buffer if you haven't been able to render into it directly. And then you draw a triangle that basically, you know, wraps your entire stencil buffer, and you let that basically let the GPU do the test on the stencil buffer, and then it fills the pixels that you want filled. Now, the good thing about this approach is that when you're using the stencil buffer, there is no overfill, because the rasterizer will very cheaply throw out all the pixels that fail the stencil buffer test. You can use conventional 2D APIs to draw that stencil buffer, and you can use fairly simple shaders once you're done. Now, if you are doing AA with, if you're using stencil buffers, you can do good anti-aliasing with MSAA. If you're using textures, where you basically have the full range of 256 levels of transparency, you can do good AA with your 2D rendering API, and you get really high quality, right? The cons are that there's no hardware benefit for generating your mask. Still a lot of CPU work there. The bandwidth requirement is high because you're uploading all these large surfaces of your stencil buffers. There's potential overfill when you're using textures, because then the pixels won't get thrown out in the stencil buffer, but you'll need the pixel shader to figure out whether they have an output value. And there's a high state change requirement. It's really hard to batch if you're using this approach, practically impossible. Now, the next one is 2D coverage computation in shaders. This approach was really made well known by a paper by Microsoft Research from Charles Loop and James Blinn. For those of you who are graphics geeks will probably know who that are. So it was called resolution-independent curve rendering using programmable graphics hardware. And what they do is they look at all these curves that we have here, and then they make these triangles, these quadrilaterals here, that basically wrap the curve. And then they process each pixel that falls within the quadrilateral and calculate on which side of the curve that will fall per pixel. So it parallelizes really well. The inside is then filled with a simple bunch of triangles, as simple as you can get them. And the outside has very few triangles, and it fills really nicely. And you get this shape over here. And there's been a lot of interest in this approach. Has a bunch of pros. The CPU work is really minimal. The implementation is fairly simple. It doesn't require complex tessellation algorithms or anything like that. It parallelizes really well because we're doing all these pixels, we're computing whether they're covered or not in parallel for every pixel. The bandwidth requirements are very small. We only need 2 triangles for an entire curve. If we're tessellating a curve, we need hundreds, sometimes thousands. And you get really high quality anti-aliasing because you can simply calculate how far the pixel shader is from the curve in order to calculate what the coverage of the curve over that pixel shader would be, over that pixel would be. The cons are that the shaders are complex, and you're running them on a lot of pixels that you are not actually filling. If you want to reduce that overfilling, you're going to have to subdivide your curves to make your triangles, your quadrilaterals, have less overlap, or have less overlap with the non-filled area. And intersections are a little hard to do. You'll just have to take that from me. Then finally, there's direct hardware implementations. The exact algorithms are implementation dependent. The advantages are that they are optimized for the available hardware. They're implemented by the hardware vendors for their hardware. They're basically magic. You just give them your 2D stuff and they make it happen. The downside is they require underlying hardware support, usually not widely supported, and they're usually not that well tested because only a couple of devices have them and nobody's using them, which is not great. So the existing implementations, which is the last part of what I'll talk about, we have the most widely used, which is Direct2D from Microsoft, which is basically their drawing API in all recent Windows versions. It's Windows only, completely proprietary, obviously. It is essentially a user mode library that wraps Direct3D. It is almost purely tessellation based. It is well tested and widely used. It's used by Firefox on Windows 7 upwards. It's used by IE since IE 9 upwards. And it's used by Steam and lots of other software that is commonly used. Then from Google, we have Skia, or Skia GL to be specifically, which is the Skia version that renders using OpenGL. It's open source. It's cross-platform. As I said, it's implemented on OpenGL. It uses a hybrid approach, so it can draw either using coverage computation or tessellation, or it can do actually upload CPU masks. So it uses all the different things, sort of. Now, currently, I don't know where Chrome is exactly using it right now, but they're not using it everywhere yet. But they're working on it. And we are also using it for Canvas on mobile devices. Now then there's, from Apple, there's QuartzGL, which is their core graphics GL backend. It's OS X only. It's used by Safari in modern versions. And as far as we know, it's a little harder to dissect. It uses a hybrid approach. Because it's not a completely user mode thing, we can't go in and see what it does, sadly. Then there's KaiWiGL. It's community maintained, open source, cross-platform, also uses a hybrid approach. I don't know of anybody actually using it in practice. As far as I know, it's full of bugs. If it ever goes somewhere, that would be wonderful. At this point, it doesn't look like it has or that it will. And then there's 2 direct hardware implementations I'd like to mention. First of all, there's an NV path rendering extension, which is an extension by NVIDIA. It requires an NVIDIA GPU, recent one, with recent drivers. It's completely implemented in hardware. It outputs, it's basically an OpenGL extension to rasterize a 2D mask to your stencil buffer. And then you just draw the outlying triangle. It's fairly new, not widely used, not widely tested. We've worked with NVIDIA engineers with it. It shows some potential, also has a couple of issues. We'll see where that goes. And then there's basically what is the specification, OpenVG. It's basically open vector graphics like OpenGL. It's by the Cronus group, just like OpenGL. And it describes an API that can be used for vector graphics rendering. I don't know of any widely used implementations. Particularly mobile vendors are looking into this at the moment to save power on mobile devices. Most information that I have on that is in this magical proprietary NDA mobile world. So I can't say a lot about it, but it is not yet widely used to the best of our knowledge. All right? that was everything I had to say. I hope it was not too technical and not too specific to graphics geeks. If you have any questions, we got a couple of minutes for that. You're all asked to, if you have a question, wait till they come to you with the microphone, because otherwise it won't get into the recording and the recording will be less useful. Yes?
Of those libraries you mentioned in the end, which ones are targets to use for Firefox and our renders into the future?
Currently, SkiaGL and Direct2D. And we are looking into NV path rendering together with NVIDIA engineers, but for now, we're not going there. Yep. Excellent. Thank you.
Thank you.
If you want to download them or look at them or anything like that.
Thank you, Bas. Hello, welcome. So please, there are a lot of people who want to enter the room. So if you can go to the middle.
Les mots que tu dis, je les connais pas, c'est genre, je saisis pas les... Ouais, mais c'est une difficulté en plus par rapport au français. Ouais, mais limite, il aurait parlé français.
Mais je ne savais pas qu'on n'était que des francophones à cette table.
Ouais, pardon quand même. Je m'en souviens toute ma vie. Du coup, là, il me regarde, genre, il me sort un truc en français. Je me dis, putain, mais tu parles français, quoi.
Tu ne pardonneras jamais.
Use her second microphone for like the right side if you want.
Yeah.
Use it because
I'm here. I can help you if you need help.
Everything's okay. For the moment.
Okay. Great.
Okay.
So now let's listen to James Graham.